So we just derived these three equations for the angular velocity of a rigid body in the absence of any external forces or moments. And these are called Euler's equations for a free spinning rigid body. Free spinning meaning it has no external forces or moments. So these are the three equations, and like I said, they are called Euler's equations. They're three differential equations, and as we saw in the previous video, we can sort of examine some special solutions for this set of equations. If the angular velocity is initially equal to zero, then the angular velocity remains zero for all time, because if you plug in zero for these guys, these become zero, so there is no change in the angular velocity. So that's a very simple special case. Another special case is if one of the components, omega xb, is not equal to zero, but omega yb and omega zb are equal to zero. Okay, so look at these equations again. If omega xb not equal zero, but zb and yb are equal to zero, then of course this will be zero. This will be zero because omega zb is zero, and this will be zero because omega yb is zero. So if just one of them, omega xb, is not equal to zero, we still have the situation that d omega xb dt equals zero, d omega yb dt equals zero, and d omega zb dt equals zero. In other words, if you have an initial condition like this, omega xb not equal to zero, but omega yb and omega zb not equal to zero, then it remains the same for all time. Omega xb of t remains whatever it started out with, and yb and zb also remains whatever it started out with which is basically zero. Okay, so if just, in other words, if the angular velocity is along one of the principal axes, right? So in this case, omega is along exb because that's the only component that's not equal to zero. So if omega is along exb, then it continues to spin about exb forever. So in this case, angular velocity remains constant. Similarly, if you pick omega to be just along EYB or just along EZB, then again, omega will remain constant for all time because the reasoning is exactly analogous, right? So these three derivatives will be equal to zero. So whatever omega you started out with will remain the omega for all time, okay? So these are special cases. Case 2, 3, and 4 correspond to special cases where omega has a component or is entirely along one of the three principal axes. Case 2 was when it was along EXB. Case 3 was along EYB. Case 4 along ECB. And the result is that the omega continues to remain in the same direction. In other words, the object will continue to spin with the same angular velocity. Okay, so that's if it's spinning exactly about a principal axis. What if we had an initial condition like this, where there is a big angular velocity component along one of the principal axes? So it's almost along one of the principal axes, the angular velocity, but then there's a small component along the other two axes, right? So big component along y, small, very small component along x and z, or big component along z, and then very small component along x and y. Okay, where these epsilons need not be the same, and they are considered to be very small numbers, essentially, much smaller than this quantity. So what happens when we essentially start with an initial condition? There is a small perturbation away from these perfect initial conditions where it's spinning along one of the principal axes. There's a famous result, and you can see lots and lots of YouTube videos on this topic, which has to do with instability of spinning about a principal axis. We will do this in Matlab Simulation and animation in the next video. We will show how spinning about two out of these three axes is actually stable, but spinning about one of these axes is actually unstable. So we'll show that and the conditions for that with the Matlab simulation. Like I said, there's lots of YouTube videos that you can watch. Like if you want to watch one, should Google something like T-nut spinning in the space station or something like that, and you'll see really interesting videos. In one of the future videos, I'll sort of play that and put that on a video lecture. And in real life, what you can do is you can take a notebook or your smartphone, if it's well protected, and try to spin it up along one of its three principal axes and try all three of its principal axes. And you will notice that two out of those three principal axes, the object will just spin nice and stably. And then the third principal axis, it will not spin persistently. So let me actually draw that picture. So if you had let's say an iPhone or a smartphone which has like a form factor like this, right? It's got three axes, and the principal axes are going to be like this, right? So these are the three principal axes. So this is out of the plane, and this is along the plane through the center of mass along the long axis, and then this is along the short axis. And I believe if you actually find the moment of inertia or about the three axes, the principal moments of inertia, you'll find that EXX let me move this over here. You'll find that EYY is the smallest, and EXX is the intermediate axis, intermediate moment of inertia, and then EZZ, which roughly is going to be the sum of EXX and EYY, is going to be bigger than either one of these things. Okay, so it turns out that spinning about, so this is literally imagining you throwing up your cell phone and then try to spin it up about this axis, or try to spin it up about this axis, or try to spin it up about this axis. I'll post a video of me doing it with my phone. You will find that stable for spin about Y or Z, but unstable for spin about X. Okay. Okay, so try spinning it about each of these three axes and see what you get. And of course, you'll have to spin it fast and don't break your phone trying to do this experiment. Okay, so that's a very famous example or result in mechanics. And like I said, we'll link you to some YouTube videos on this topic. Okay, how do you actually do a Matlab simulation and animation for this free spinning rigid body? If you actually wanted to do a simulation of this and see this in Matlab, how do you do that? Of course, we just derive these differential equations. Equations number 4, 3 differential equations for the omegas. So let me go back here. So those equations determine how the angular velocity omega evolves. Okay, it's represented in the body fixed frame B. So if you're given initial conditions in the body fixed frame, we can compute the omega as a function of time also in the body fixed frame. So that's straightforward. You just integrate those 3 differential equations. Relatively simple looking differential equations. Now, But that's about omega, the angular velocity. How do you use this to get an animation of the 3D spinning motion? In other words, how do you keep track of the 3D orientation of the object, right? So you know the angular velocity, but what about the 3D orientation? In other words, the angular position, so to speak. So we need to keep track of the 3D orientation somehow, and this is why we built up this infrastructure, talking about rotation matrices, Euler angles, quaternions, and things like that. We'll just use rotation matrices to keep track of the 3D orientation. Okay. So, um, so what we need to do is essentially write a differential equation for the rotation matrix that describes the motion of this 3D object, the orientation changes of this 3D object. No, recall that we already did this a few lectures ago. Recall that if you had a vector fixed in the body, for instance, the vector from G to P, the center of mass to some point P, and you represent that vector using body fixed coordinates like this. And you can also represent the same vector in some global coordinates or the inertial frame, the non-rotating frame. If these two sets of coordinates are rotated by some rotation matrix Q, then this is the thing that we derived a few lectures ago. We showed that the rate of change of this rotation matrix Q is given by this matrix. This is an angular velocity skew matrix, and Q is again the rotation matrix, right? So this omega matrix represents a skew tensor. It is you take the angular velocity vector represented in the zero frame and construct the skew symmetric matrix, and the rate of change of this rotation matrix is given by this differential equation. Okay, so what is this rotation matrix? It takes you from the body fixed coordinate frame to the non-rotating frame, right? So this is a rotating frame that rotates with the body, and this allows you to go from the rotating frame to the non-rotating frame, right? So that's the rotation matrix. Now, what we do is, for convenience, we choose the initial orientation of the body fixed frame to be aligned with zero, namely the non-rotating frame, right? So initially at time t equal to zero, the zero frame is exactly the same as the body fixed frame. That's just an arbitrary assumption that we're making. So that the bx, by, bz, namely the position of any point in the body fixed frame, is actually the initial condition of R P with respect to G of any point, right? So what this means is this Q represents the transformation from the initial position to position at any point in time, okay? And Q, because we chose the frame B to be the initial, it is identical to frame 0 initially. Initially, Q starts out being identity, okay? So you can think of Q as the rotation matrix that takes you from B to O, which is sort of what we defined, right? So rotation matrix that takes you from B to O, like here. And it's also the rotation matrix O to B transpose, okay? Okay, so that's the premise. We are trying to describe the motion of the rigid body using a rotation matrix that describes the transformation from the body fixed coordinates to the non-rotating frame. Okay. Okay, so now that we have a differential equation for the rotation matrix. In other words, the rotation matrix, the rate of change of the rotation matrix is given by, is a function of both the rotation matrix and the angular velocity. In other words, if we knew the angular velocity, we can compute how the rotation matrix changes. Okay, so if the rotation matrix starts initially from identity, in other words, no rotation, and if we knew how the angular velocity changes as a function of time, we can compute how the rotation matrix changes as a function of time. Of course, this equation depends on angular velocity vector expressed in the zero frame, the non-rotating frame, and then we can, using essentially these rotation matrices, compute how to go from the body fixed frame to the non-rotating frame, right? So, okay, so in summary, what we have are these three equations, which we call the Euler's equations, and then this equation for the rotation matrix. But this equation is actually 9 equations because Q is a 3 by 3 matrix. On the right-hand side, of course, will be a 3 by 3 matrix as well. So this is actually 9 equations, 9 scalar equations. What we might do in the context of ODE 45 is actually take this 9 differential equations, which are arranged in this case as a 3 by 3 matrix, and then just string it out as d by dt of q11, d by dt of q12, etc. In other words, make them 9 scalar equations separately. But we'll do that in Matlab. And like we said, here we are integrating omega in frame B. Here, the rotation matrix depends, change of rotation matrix depends on omega in the non-rotating frame, but we can go between those two things again using Q, right? Okay, so these are the equations that we have. So 3 plus 9, 12 equations, 12 differential equations, and then some algebraic relationships between them, between some quantities in them. And then we have some initial conditions. Initial conditions can be some initial angular velocity, say expressed in the B frame. Sometimes you may know the angular velocity in the zero frame, but of course you can use this transformation matrix to convert between the two. Anyway, so the angular velocity is given. Let's say the rotation matrix initially is the identity, no rotations. And that's it. We have differential equations, we have initial conditions, and we can solve this equation. Just as an aside, these three are principal inertias of the rigid body, and in the Matlab example, what we're going to do is use a cuboid with mass, let's say m 1 kilogram, L equals 1, B equals 2, H equals 3, so that we get an object with non-identical principal inertias. These are the formulas for the principal inertias for a cuboid, which we can compute. And the important thing to recognize is that these are all different. Okay. To simulate these equations, we can ignore the motion of G. The velocity of G does not really affect the rotational motion of this object. So we're going to ignore the translational motion, if any, of the object and just focus on the rotational dynamics. Okay. So between here and here, what you should do is probably look at the Matlab code example and come back to this video. Matlab code that does a simulation of the differential equations and then an animation of how this spins under different conditions. Okay, and what you will find is what we described earlier. In this case, Ixx is greater than Iyy is greater than Izz. This is the intermediate principal moment of inertia. In other words, principal moment of inertia of intermediate magnitude, not too large, not the largest, not the smallest. And you will find that if you start the object spinning close to the x-axis, it will remain close to the x-axis. If you started off close to the z-axis, it will remain close to the z-axis. But if you started off close to the y-axis, you'll find that it will spin about the y-axis for a little bit and then do a complete flip and start spinning about the negative y-axis, and then do a complete flip and then start spinning about the y-axis, and so on and so forth. So has this like sort of long-term oscillatory dynamics in addition to the spinning motion, which is sort of interesting. This instability, if you will, can be understood analytically through sort of geometric methods, or you can use classical stability analysis, which is the subject of a different course that I have taught in the past, to sort of show stability of spinning about these three axes. So it's possible to show this rigorously with pencil and paper calculations. Maybe I'll post a video on that topic separately. Okay, so but ideally between this and this, you should have watched the Matlab simulation videos and perhaps even YouTube videos on this topic.